Welcome everyone to our webinar today, Disinfection Byproduct Control with Permanganate. Our speaker today is Darren Scott and I am Liz Mueller. A few housekeeping items before we get started. We are recording this webinar and everyone will be kept in listen-only mode to help cut down on any background noise. So we encourage you, if you have any questions, to submit those throughout the presentation when you think of the question into the question pane of the GoToWebinar panel. You can also email us directly, especially after the webinar, if you think of any questions, and we will get back to you. If you submit a question and we don't get to it, we will have your information and we'll be able to send that to you as well afterwards. Here is how to find us. We have a few ways. We've listed our website and our general sales and marketing email address, as well as our marketing team, Ashley Swingle's email address here. If you don't currently receive our email blast for upcoming webinars, presentations, trade shows, or any technical information, you can sign up on our website or also let us know and we can get you added to that join our email list. We also can't forget to mention our social media platforms. We encourage you to connect with our Carus page as well as our team members on LinkedIn, where we're often sharing upcoming events, including webinars, articles, or news from the industry. Listed here are links that you can find on our website that you can view any upcoming webinars and then also any of our recorded webinars. And at this time, I'd like to take this opportunity to introduce our speaker, Mr. Darren Scott. Darren has worked for Carus for over 20 years. As the technical marketing specialist, Darren conducts laboratory testing and product demonstrations for Carus municipal, industrial, and environmental customers and prospective new customers. These product demonstrations include technical training, safety presentations, and installation of safe chemical handling and dosing systems. He is a graduate of Illinois Wesleyan University, Bloomington, Illinois, with a Bachelor of Science degree in Chemistry, ACS certified. Mr. Scott is a member of AWWA, Water Environment Federation, and the American Chemical Society.
Thank you, Liz. Good afternoon, everybody. A brief outline of what we're going to talk about. We'll talk about the options you have for permanganate products when you're looking at disinfection byproduct control. We'll specifically then talk about the rule itself, how you go about doing demand jar testing, and then finish up with several case studies of successful applications in the field. So you really have two options when you're using permanganate for disinfection byproduct control. You can use Carus Potassium Permanganate, which is available as a dry crystalline material that you can use. Pictured on the right-hand side of the screen, you can see it looks like purple sand, and even close-ups, it even looks darker purple. Carus is potassium permanganate based. You're only going to typically find it in the field in granular crystal form. It has a very high bulk density at 90 to 100 pounds per cubic foot. Shelf life for this product is stable, and it will keep indefinitely stored in a cool, dry area in closed containers. Meaning if you have this product in a sealed container a year from now, 5 years from now, 10 years from now, it's still going to be the same percent active during that time. Carus Potassium Permanganate is typically greater than 97% active as the dry product. Now you may ask yourself, why do you find Carus Potassium Permanganate only in the dry form? Well, it's really because of the solubility of potassium permanganate. At room temperature, the max solubility for potassium permanganate is 5% in solution. Most customers are going to use the permanganate in one of two ways. They're either going to make a batch of permanganate solution. Typically when they do that, it will be a 3% solution that they make. That'd be a 1/4 pound of dry permanganate per gallon of water. And they might make up a 100-gallon tank, a 1,000-gallon tank, size of that solution, and then meter that into their application point. You're going to need a mixer in that tank and at least a good 15 minutes of mixing to get a 3% solution concentration. Now, available packages, the product is available in 55-pound pails, 330-pound drums, and 3,300-pound cycle bins, along with bulk. And we have customers that use all those different packages depending on their application. The other main product that you have when you're using permanganate would be Carus liquid permanganate, which is sodium permanganate based. It's going to look like a dark purple solution, but then as you dilute it down, it's going to take on the same purple characteristic that potassium permanganate solution would as well. Carus liquid permanganate is only available in the liquid form. You're never going to find it in a dry form. It's sold as both a 20% solution and as a 40% concentrated solution. The same thing here though as with the dry product. The shelf life for the Carus liquid permanganate is stable. It will keep indefinitely if stored in a cool, dry area in closed containers. So if you buy the product in drums or totes or bulk, 20%, 40% solution, it will stay at that concentration a year, 3 years, 5 years from now. It will stay at that same exact concentration. Generally, we recommend that customers plan on holding the product for about a year and then turning their stock over in a year. But we do have some customers that buy bulk and it takes them 2 years to work through the bulk tank. And there's no loss in strength during that time. Now, one of the reasons that we would sell the Carus liquid permanganate at a higher concentration is because of the switch from potassium permanganate to sodium permanganate, we greatly increase the solubility in water. So you can see the curve here, which allows us to sell both 20% and 40%, and they'll be that way at room temperature. The product is available, like I said, in 55-gallon drums, 250-gallon IBCs, and bulk. And it's probably pretty typical for our customers to either have a bulk tank or to purchase it in the IBCs. One thing to keep in mind when you're handling permanganate is when you dose it into the drinking water, it's going to have a very distinct characteristic color to it. Depending on the level concentration you have, it's going to look faintly pink at low levels of 0.5 to 1 milligrams per liter. And then as the concentration goes up to 5, 50 to 100, it's going to look much more purple in coloration. The sodium permanganate at 20% and 40% looks dark black because of how high the concentration is, but as you dilute it down, it will take on the same purple color characteristics. One thing to keep in mind is when we talk about permanganate concentrations, we're really talking about the concentration expressed in milligrams per liter, which is also equivalent to parts per million when we talk about a dosage. Now, there are some industry standards out there for the application of permanganate into drinking water. There is the AWWA B603-16 permanganate standard that lists what quality product you should get for both potassium permanganate and liquid permanganate / sodium permanganate out there. Our product meets the NSF standard 60 for a drinking water additive, and you will see it on our literature and on our product labels on our containers as well. You want to make sure for a drinking water application that you have the NSF standard 60 certification in order to use it in your drinking water plant. Now, when we talk about permanganate being used in drinking water treatment, there's a lot of applications, and we're specifically going to talk about disinfection byproducts today. But also keep in mind that as permanganate's reacting with things that can cause disinfection byproducts, there also are other components in the water that you will react with. Probably the quickest things to react are iron and manganese oxidation. You also have several taste and odor compounds that will react immediately. And depending on if you have colored water coming in the door, you may react with some of the things causing color. And then in groundwater applications, you would have a reaction with arsenic and some absorption of radium onto the manganese dioxide you form. So one of the things you want to keep in mind when you're applying permanganate for disinfection byproduct control, you need to keep in mind that we will also react with these other constituents in the water as well at the same time. So how do you get disinfection byproducts in your finished drinking water? Well, you've got two ways that it happens. You've got the addition of a disinfectant, which is typically going to be chlorine to the water. And you may use that in your pre-oxidation process at the front of the plant to oxidize iron and manganese or oxidize some taste and odor compounds. And then you're also going to reapply the chlorine at the back of the plant, usually right before the filters or right after the filters, for your final disinfection. Well, that chlorine, when it comes in contact with natural organic matter, can form THMs and HAAs. And that reaction is irreversible. Once you form the THM and HAA, you're then either going to have to remove it after you formed it or not form it in the first place. Now, the two places that you will form THMs and HAAs from can be the natural organic matter that's in your source water. So if you have a lot of TOC in your raw water, you also have an algae bloom, that can contribute to more natural organic matter coming into your plant. And then if you chlorinate that, you'll definitely have higher THMs and HAAs. The other place it can be is once you feed your free chlorine out to the distribution system, there can be biofilms that are growing out in the distribution system, and you'll continue to form THMs and HAAs as that free chlorine reacts with the biofilm out in the distribution system. So those are the two places that you'll get the disinfection byproducts from. Now, when we talk about the two types of disinfection byproducts, there's trihalomethanes, THMs for short, and there's 4 of them that we measure in order to meet the regulation. Typically, if you're feeding free chlorine, chloroform is going to be the one that you're going to see at the highest level. But what they'll give you in your report is a total trihalomethane number, so a THM number. But usually chloroform is the one that's the highest. With haloacetic acids, HAAs for short, the regulation measures 5 of them, and you'll see a spread across them. Typically, they're referred to on your report as HAA5s, and it's these 5 compounds that they measure. So there are currently 2 rules that regulate disinfectants and disinfection byproducts out there for drinking water plants. The stage 1 rule was to reduce the exposure to disinfectants and the disinfectant byproducts out there. The original regulation was put into effect because there has been links between disinfectants and their byproducts that can cause increased rates of cancer from people that drink the water over a lifetime, and also reproductive effects like miscarriages. The stage 1 regulation affects any water system that adds a disinfectant during any part of the drinking water treatment process. So basically, it regulates all water systems. The stage 1 regulation established the maximum contaminant level, MCL, for total trihalomethanes at 80 parts per billion, and for total haloacetic acids at 60 parts per billion. The monitoring requirements for the stage 1 regulation were samples were taken quarterly, and you were allowed to do a system-wide running annual average. Now, all systems were supposed to be in the stage 1 compliance by January of 2004. So this rule has been on the books for a long time. The stage 2 rule built on the stage 1 rule and established a couple different things that systems were going to do to be in compliance. There was an initial distribution system evaluation, meaning you were going to go back out and do evaluation of sites with high disinfection byproduct concentrations. The old rule basically established that each site was valid for both THMs and HAAs. The new evaluation had you determine which sites were the highest for THMs, which sites were the highest for HAAs, and you might have separate sites for each of them in your distribution system. Also, the bigger change was it was a locational running annual average, what meant you needed to monitor and meet the MCL at each individual location. So you weren't allowed to average the whole system together anymore. The rule was finalized in 2006, and in 2013, all systems were to comply with the stage 2 disinfection byproduct rule. US EPA and many state organizations have stated that the disinfection byproduct rule is one of the most violated rules in the US after it went into effect, followed closely by the lead and copper rule as well. So these are 2 rules that municipalities still struggle with today. So there are a couple different disinfection byproduct control strategies that you can take. Obviously, if you're using chlorine at the front of the plant for pre-oxidation, just moving that chlorination back to the back of the plant, either right before filtration or right after filtration, can reduce the amount of disinfection byproducts that you form, because your coagulation process in your plant is designed to remove organics. You'll get TOC reduction, natural organic matter reduction at the front of the plant. So allow that process to remove those compounds and then add your chlorine at the back of the plant where you have lower levels. What to keep in mind though is if you are using chlorine as your pre-oxidation, you're no longer going to have it there to oxidize iron and manganese to remove it. You're not going to have it there to remove taste and odor compounds. So you'll probably have to add something else as a pre-oxidant at the back of the plant. Also, by moving the chlorine, you're delaying your disinfection. So you need to make sure that if you're going to move it back, do you have enough CT credits to get your chlorine contact time at the back of the plant in your clear well to meet that standard. Now, one of the ways you can replace chlorine at the front of the plant is pre-oxidation with permanganate. Ideally, we would love to apply the product at the front of the plant or, if available, at the raw water intake. What this allows is the permanganate to react with the natural organic matter in the raw water. That will modify it. Your then coagulation process will then precipitate the natural organic matter out of the water. And now when you get to your chlorination point at the very back of the plant, before filters or after filters, you'll have a lower chlorine demand because it won't be reacting with that natural organic matter. Typically, by applying permanganate at the front of the plant, you can see another 5 to 20% reduction in disinfection byproducts, but you're also going to be able to control your taste and odor compounds and your iron and manganese at the front of the plant. One thing to keep in mind when you're applying permanganate at the front of the plant is we form no disinfection byproducts. The other preoxidants that are used, like chlorine dioxide, has a disinfectant of chlorite that you have to measure on a daily basis and has an MCL. And then if you're feeding ozone, you also have an MCL on a monthly basis for bromate. So the other preoxidants you can use do have other disinfectant byproducts that you need to look at, whereas permanganate does not. So when we first talk about using permanganate for disinfection byproducts, we really want to talk about how do you establish a dosage. And the easiest way to do that is each water is going to be unique, and you're going to want to do a permanganate demand jar test where you dose various levels of permanganate to determine how much permanganate makes sense in your plant based on your application point. Like I mentioned earlier, the best treatment plant injection points would either be at the raw water source. So if you have a lake or a reservoir and you have a pump station there where you can put permanganate in and feed it there, that allows you to have all the reaction time as the water carries into the rapid mix at the plant. Some plants will be based right at their raw water source, so they're right on the lake or reservoir, and there's really not much time gained by feeding because maybe you only gain 60 seconds or a couple minutes before your rapid mix. In that case, then definitely add it at your rapid mix at the plant. Permanganate then has time to react in the rapid mix and in your flocculators, and ideally your control point would be to have no permanganate residual carrying into the sedimentation basin because you want the manganese dioxide that's formed to settle out in your settling basin. So you'll feed the permanganate in that very first part of the plant, the rapid mix and the flocculators. There are several factors that affect the permanganate reaction. So you'll want to do this jar test right on your site where you're going to do it. Some of the things to keep in mind: what are the concentration, what oxidizable material do you have in the water at your application point? One of the easiest things is how much soluble iron and manganese do you have coming in the door at the front of the plant. You can calculate that demand pretty easily. The organics is something that you'll want the jar test for. How much time do you have for the reaction? Do you have 20 minutes of contact time? Do you have 60 minutes of contact time? Run the jar test for the full amount of time to determine how much permanganate you can feed. What's the temperature of the water? Typically in warmer weather, permanganate reacts quickly. You'll have a higher demand. Plus also in the summer months, you might have algae blooms and other things that will increase the demand at that time. And then also pH affects the quickness of the reaction. Higher pHs make permanganate react quicker. So if you're in the mid 7s, that's better than being in the low 6s. Typically, we want about a minimum for disinfection byproducts of about 15 minutes. We do need some time to react with the organics and to form some manganese dioxide, which then your coagulation process will grab onto and then it'll settle out in your settling basin. You do want to try to separate some of your treatment chemicals. If you add permanganate at the same time that you're adding carbon, carbon will absorb some of the permanganate residuals, so you'll lose a little bit of the effectiveness of your permanganate by feeding them at the same time. Also, ideally, you'd like to be before your polymer addition or coagulant addition so that you form some solids prior to your coagulation. And then ideally, you really don't want to feed chlorine at the exact same point as permanganate, because as you're reacting with your organics to remove them, if you're feeding chlorine, you'll also form THMs and HAAs at the same time. And once you've formed a THM or HAA, permanganate can't react with it any longer to remove it. So you really want that reaction done prior to adding the chlorine. Like I said, if you feed at the raw water source, you probably want to carry a slight residual into your rapid mix. If you're feeding at your rapid mix in your plant, you probably want to carry a slight residual to the end of your flocculators, usually somewhere between 1/10 and 2/10 of a part. The jar test that we typically use in the field for determining how much permanganate to feed for disinfection byproducts, we call a permanganate value method. What we're going to do is we're going to look at how much permanganate can be consumed in a specific amount of time. And that will take into account the temperature, the pH, how much permanganate you've added, and then what type of oxidizing materials do you have in the water. What we'll do for this test is obtain raw water and then immediately do the jar test. Record the temperature so you have an idea whether it's cold water or warm water when you're doing the test. Separate out your sample. Typically, we'll run somewhere between 3 and 6 1-liter samples. That allows us to vary the permanganate dose. The more jars you run, the closer together you can have the permanganate residuals. What you want to keep in mind is typically we're going to dose somewhere between 0 and 3 milligrams per liter. And ideally, usually 0 to 2 is probably where most plants fall. So usually somewhere between half a part, 1, 1.5, 2 parts for it. Now, when you're dosing the permanganate into the jars, you do want to give yourself a few minutes between the doses so that you can come back and measure residual after your set time. One of the first things you do when you're setting up for the jar test is where are you going to apply the permanganate, and then where do you want to have permanganate residual, so how long. So if you're feeding it the rapid mix and the detention time in your plant between rapid mix and flocculators is 30 minutes, then you'll want to run this jar test for approximately 30 minutes to give you an idea of how much permanganate residual you can carry for that 30 minutes. After that set amount of time of 30 minutes, you can come into each jar and measure your permanganate residual. A lot of times when you're running this jar, because you've got plenty of sample, you might actually run several different times. So if your full time is 30 minutes, you might run one at 15 and then another one at 30, just to see how much difference you have or how much permanganate is reacting over time. Now, when you're measuring permanganate, there's a couple different ways to do it, but the easiest way in the field is to use the DPD powder pillow that you use for free chlorine. Depending on the instrument you have, will determine what powder pillow you're going to use, but we're really using a modification of the chlorine DPD powder pillow in order to get a permanganate residual reading. Keep in mind, since we are using the DPD free chlorine powder pillow, that if you have chlorine or ozone or chlorine dioxide or manganese dioxide in the sample, it will interfere and color the powder pillow. What you're going to do is obtain a sample of that water from the jar. If it's in the part of the process where you have the coagulant, well, then you're already going to have the coagulant added so that you can bind up any turbidity and remove it. And then you're going to want to make sure that you filter this sample to remove the solids, because that will skew your results high. After you filter the sample, zero the spec with the filtrate, add your powder pillow, mix it, and then immediately read it. Based on the reading that you have, it depends on what product you're using. if you're using potassium permanganate, you need to multiply your DPD reading by 0.89 to determine how much actual permanganate is there, because there is a slight difference between chlorine readings and permanganate readings. If you're using sodium permanganate, the reading actually ends up being the same for that. You will see the same pink color that turns darker red when you add the powder pillow to the sample. What you can do after you've done the jar test is your permanganate demand in all those jars can help you draw a line. So in this case, it was a surface water plant with a 15-minute demand, and we came back at 15 minutes and measured jars that had 1 part, 2 parts, 3 parts, 5 parts of permanganate in them, and then saw how much permanganate each of those jars consumed. Drawing the graph tells you that roughly in 15 minutes, based on the jars, they would consume about 0.4 milligrams per liter of permanganate in that 15 minutes of contact time. So this gives you a dosage where you would start in the plant at 0.4 milligrams per liter, and 15 minutes later you would have no permanganate residual left. So it's a good way to establish your initial dosage. Once you start feeding in a plant, you can then measure residual in the plant at a control point and then adjust your dosage without having to go back and do the jar test repeatedly. The only time you would repeat the jar test is if you think there's a significant change to your demand, and maybe you want to do a jar test just to confirm it before you turn it up in the plant. So we have several different case studies with our different products looking at disinfection byproduct removal. Our first case study here was a plant that was looking at Carus versus free chlorine. And they had really 2 types of issues in this plant. They were a groundwater plant under surface influence. They had 5 MGD that they treated through 2 separate 2.5 MGD active flow treatment trains. So the water came into the plant and split into the 2 processes. Because they were under surface influence, the raw water manganese could vary depending on what was happening in the area. So if they had a lot of rainfall and runoff, the manganese would spike. And then if they didn't have that, the manganese would go down to a lower level. Now they had tried using chlorine to remove the manganese in the plant, and because they had to feed so much chlorine to oxidize the manganese, their THMs were over 80 parts per billion leaving the filters in the plant. So they were already in violation of the regulation before they'd even gone out to the distribution system. So they really wanted to look at, is there something that we can use to lower the manganese quickly in our process, and then also not form any THMs during that part of the process. As you can see here in the picture, the infiltration wells are the gray squares that you see there, and then the mound of dirt in the background is the river that's passing by. So obviously they're getting riverbank filtration, but obviously if the water quality shifts in the river, that shifted the water quality in the plant. Their trial equipment was a tote of Carus with a metering pump on top of it that they could feed directly to the rapid mix in the plant. At their rapid mix, you can see we had the injection quill is in the gray PVC line that's duct taped to hold it below the surface, but you can see the characteristic pink color of permanganate as we applied it at the bottom of the rapid mix. As the water comes up and separates into 2 processes, both sides are the distinctive same pink color. In the active flow process, we go from the flash mix where they're adding the permanganate, they're adding their polymer, and they're adding sand. They then go to a mix chamber where the sand and polymer stick together along with any solids. From there, they go to a lamella separators, and from there they go to their finished water, drinking water filters. In this plant, between 10 and 20 minutes from the front of the plant to going to the filters as far as contact time, depending on what flow rate they were running at. So they treat their water quickly and have to get it out the door through the filters. When they were applying free chlorine, one of the things they struggled with, because the manganese level was variable, they would really have to crank the chlorine dose up to try to get the manganese down. There were times when they couldn't get the chlorine high enough based on their feed system to get all the manganese out, and so the water would go into the clear well at about 0.12 milligrams per liter as manganese. And then as it continued to react with the chlorine, they'd get brown colored water in the clear well. With the sodium permanganate at the front of the plant, we were able to get the manganese going to the clear well down to 0.02 milligrams per liter, so very low, below the 0.05 standard. Also, because permanganate doesn't form any disinfection byproducts, going into their clear well, their THM level was at 0 versus above 80 when they were feeding chlorine. So we had knocked the THMs down before they added their final chlorine to the clear well. Our second case study here, also looking at THMs, was Elsinore Valley Municipal Water, a 37 MGD facility, and they had THMs that could be as high as 130 to 140 parts per billion, and they also were getting some musty and fishy odor complaints out in the distribution system. Their treatment at the plant was anywhere from 2 to 3 milligrams per liter of potassium permanganate. Now, when they did this study, they looked at two things. With chlorine at the front of the plant, at the flash mix, they had about 38 parts per billion of THMs. Settled water had about 60 parts per billion of THMs. And then finally, filtered and clear well water was in the 130 to 140 range going out the door. So well above the 80 parts per billion. By moving the chlorine back to the filter, you had no THMs at the front of the plant, but they needed permanganate to remove that musty, fishy odor that they had in the water and also remove any iron and manganese, but we had no THMs. And then at the back of the plant, you can see that we dropped from 130 to 140 down to 35 and 40 parts per billion. So a very massive reduction in the THMs going out the door at the plant. So as you can see, that 140 to 40 part per billion reduction by moving the chlorination point and adding permanganate to the pre-oxidant was about a 70% reduction. Also, the switch from pre-chlorine at the front of the plant to permanganate also reduced the taste and odor complaints they had from 5 to 10 per month to 0. So they also were getting better taste and odor control at the plant after treatment. So a dual benefit. Our third case study, switching it up a little bit, this plant was specifically looking at control of halogen acetic acid, HAAs. It was a Southern Illinois water treatment plant, and they were surface water, about a 5 MGD average, and they were having issues with halogen acetic acids in their finished water, anywhere from 14 to 150 parts per billion. They wanted to look at a couple different strategies for treatment. They wanted to get their HAAs to less than 30 parts per billion, so well below the 60. And during that evaluation, they wanted to look at moving the pre-chlorination point to the back of the plant, and then also look at what would chlorine dioxide do as a pre-oxidant, what would potassium permanganate do as a pre-oxidant, and then also what happens if we use free chlorine and then add carbon to absorb the HAAs that are formed. So a couple different treatment options. They looked at this over the course of many months in different kinds of treatment levels. You can see that as the water temperature warmed up coming into the summer months, you also typically see increased organic loading in a plant, that the HAAs climbed during that time. So they started May around 20, they increased to 30 parts per billion, then 45 by the end of June. So the numbers were rising. They started to feed permanganate at the front of the plant at about a 0.5 milligram per liter. That did knock the HAAs down some, from 45 down to about 30. As the water continued to warm up, they started to see the levels still climb back up to 45. So they increased the permanganate dose to about 0.75, and then finally up to about 1 milligram per liter. And you can see the HAA started to drop back off again as we remove some of that organic material. What they looked at was all three options that they had considered: potassium permanganate, powder activated carbon to absorb the HAAs, or chlorine dioxide as the pre-oxidant. All of them would work to help them keep HAAs under control. But when they looked at the cost per 1,000 gallons, permanganate ended up being the cheapest cost per 1,000 gallons that they were treating at 0.011. Carbon was just a little short of double, and chlorine dioxide was just about double the cost. So obviously permanganate was the cheapest option and got them control of HAAs. Permanganate at this plant effectively could replace chlorine as the pre-oxidant, so moving the chlorine to the back of the plant. They were really focused on HAAs, but they also noticed that THM levels went down with permanganate as the pre-oxidant. Some of the other concerns they had was because they were using pre-chlorine, they had pretty good control of taste and odor compounds. When they switched to the permanganate, would that work for the same compounds? They noticed the exact same control for taste and odor compounds, so they didn't have an increase in complaints. They also were oxidizing any iron and manganese that was coming into the plant, so there wasn't any concern there from iron and manganese making it through the plant. One thing they did notice when they started treatment was they actually saw that because we were adding permanganate and forming manganese dioxide solids, they actually had a slightly better floc settling rate, which helped them with their coagulation process. So they got better settling in their settling basin before they went to filtration. So they saw a little bit of a secondary benefit. Our last case study here was Carus for THMs and HAAs. It was a southern US water treatment plant, averaged about 27 mgd on a day, and it was surface water directly from a river. They looked at moving the pre-chlorination point to above the filters from the river intake, and they wanted to start by applying sodium permanganate at the river intake at half a part. The engineer in the plant wanted to look at two separate tests in this plant. So we looked at a winter test. So in the coldest months of January and February, what kind of benefit would we see? And then they also looked at a summer test, and you'll see that in both of these slides. In the winter test in January and February, typically THM and HAA levels are lower, and you can see across the board that their system average was about 50 for THMs in the winter and about 30 for HAAs. By moving the pre-chlorine and adding sodium permanganate in the front of the plant, we could drop the THM level by about 30%, and we could reduce the HAAs by about 50%. We came back and ran a second test in July and August where the THM levels were higher, and you can see we have a system average now of 115 for THMs and HAAs at 77, so much higher than the winter months numbers. Feeding the sodium permanganate at the front of the plant, moving the pre-chlorination point, you can see that we still got a reduction of about 30% on the THMs and about a 66% reduction on the HAAs. So the reduction was a little bit better in the summer on HAAs. If you combine the two tests that we ran together, so the winter test and the summer test, so that would be 2 out of the 4 quarters that you would typically do in a year, we wanted to look at what the numbers would be as far as being in compliance with both stage 1 and stage 2. As you can see, with just 2 quarters instead of 4, the THM number was slightly over 80 parts per billion. The HAAs was below 60. So if you average in extra quarters that are low, you probably would have been in compliance with the system-wide average. But you can also see that the individual sites are quite high. So you probably would have had violations under stage 2. Combining those 2 quarters with sodium permanganate at the front of the plant, all the sites were going to meet the stage 2 regulation at the plant. What they decided at this plant was they were going to replace chlorine at the front of the plant, and they were really only going to need to do it during the summer months based on the numbers we generated during the trial. If we were able to lower those numbers for THMs and HAAs in the 2 quarters in the middle of the year where the numbers were the highest, that would be enough to get them into compliance with both stage 1 and stage 2. And then they could go back to their pre-chlorine during the winter months and still be fine. Some of the operators had concern about feeding permanganate because it did make the water pink. So were we going to have taste and odor control? Were we going to have good iron and manganese control? And what got set up during both of those trials was, here's where we're feeding, And here's on an hourly basis at the initial time we started the trial of what the permanganate residual is leaving the flocculators. And then once they got comfortable with the dosage, they went to once a shift. So once every 8 hours, they were measuring the permanganate residual. But overall, we could see a reduction of about 30% in THMs and 65% in HAAs. So permanganate has been used for many years in drinking water treatment plants. Over 100 years, Carus has been in business. Many surface water plants use permanganate. One thing to keep in mind when you are applying permanganate, because we're going to generate manganese dioxide, we need at a minimum filtration, and in most cases, it's best to run your plant with clarification and filtration. So you'll want to add a coagulant and then filter the solids out at that point. It can be very small systems, 1 or 2 mgd, to very large systems, 30 mgd, 50 mgd, that apply permanganate. The benefits of permanganate oxidation chemistry are numerous. Obviously, we're talking about compliance with the disinfection byproduct rule, but you can see with each of the plants, they also had other issues. Maybe it was a taste and odor issue, maybe it was an iron and manganese issue as well, and permanganate is going to treat all those different application points. So one product can get you multiple things under control. Ideally, you apply permanganate, you remove those off flavors and tastes from the water, you remove the iron and manganese in the process, and provide overall better water quality going to your clear well and then out the door to your end use customers at that point.
All right, thank you, Darren. And here we have our contact information. So on the left-hand side, you can see our regional sales managers by territory, as well as their phone number contact information. We also have our international contacts here on the right. All right, and just a reminder, if you have any questions, go ahead and type those into the question pane. And we will be able to share the recording and a PDF of these slides. If you're interested, just let us know. All right, we have a question that came in. What is the pH of water after applying permanganate? And what is the ideal drinking water pH?
So typically we're not adding much permanganate. So usually 0.5 milligrams per liter to 2 milligrams per liter. So whether you apply potassium permanganate or sodium permanganate, you're not really going to adjust the pH of your finished water. The reason we talk about pH is because if you're in the 7s, your reactions are pretty quick with permanganate, and you'll form manganese dioxide, which then can coagulate pretty easily. Higher pHs work better. So one of the tricks for iron and manganese removal is if you raise the pH up into the 8s, the reaction goes even faster, and you form kind of more better solids that will coagulate better. What happens is in a lot of places where they have a low pH water, so you're below pH 7, you might also have a lot of organics, TOC in the water. What happens is the reaction slows down, you form kind of pin flock, so it's a little harder to coagulate there, so you're going to want to tweak your coagulation process. Ideally, most people send water out the door between pH 7 and 8 normally. If you're going to do pH adjustment to a higher level for, like, say, lead and copper, if you do that earlier in the process, that just benefits permanganate by having a higher pH earlier. So,
all right. We have another question. Can you determine how much reduction you can get from DBPs in a jar test?
Yeah, so we talked about doing the jar test to determine how much permanganate you're going to feed in your plant. You can do, it's a little more complicated for the jar test. What you'll do is you'll do that initial jar test to determine how much permanganate you're going to feed. Then once you have that dosage established, you'll do a couple different jars at that same dosage. And then at the very end of the dosage of permanganate, you'll then want to use free chlorine and dose chlorine to each of the jars, and then put them in sealed bottles, brown amber bottles, and then allow them to sit for 24 hours. And what you'll do is you'll do one without permanganate treatment and that chlorine dosage, and then jars with the permanganate and the chlorine in it. And then what you can look at is how much THM did you form and HAAs in each of those jars after 24 hours. It's really called a formation potential test. So a lot of times the jar number will be much higher than what you see in your distribution system. But what it does give you is you'll be able to see, okay, if I just use chlorine, what is my number for THMs and HAAs? And then if I use a two-stage permanganate then followed by chlorine, what level does that drop off to? So it can give you an idea of what the system will do. So it's a way to do it. You're going to have to send that out to a local lab for THM and HAAs, but generally, you'll run somewhere between 3 and 6 jars and then have an idea of what your trend line is.
All right, great. Looks like no more questions have come in. Just as a reminder, Darren's contact information is here, as well as our Carus information. So if you think of any questions after or need any additional information, please reach out to us. We thank Darren for presenting, and we thank everyone for joining. Thank you.